All right, lecture 60, angular momentum. Now, angular momentum is necessarily a kind of a three-dimensional quantity, and that's going to make it a little bit more complicated to discuss. And so we're not actually going to talk about very much today. I'm not going to show you a lot of physics, but we're going to go into a good bit of detail and try to understand this concept of angular momentum. From last time, you'll recall the moment of inertia. We derived that expression from a consideration of conservation of energy for a system of particles. These particles were moving in general directions. Some of those directions contributed to a rotational motion that gave rise to the rotational part. The moment of inertia is analogous to mass in linear motion, but moment of inertia is for rotational motion. So, who remembers the definition of momentum?
Mass times velocity.
Mass times velocity, correct. P is equal to m times v. I actually wanted to write slightly more like this. P equals m times v. Angular momentum we described with the letter L. I have no idea why. Check into that. Probably a French word. And it's equal to I omega. Right? All I've got here is I've replaced the linear quantities, mass and velocity, with their angular counterparts, moment of inertia and radial velocity. Right? Who remembers what omega is? Well, v, or velocity, is delta x over delta t, right? That's a displacement over a time interval. Omega is a delta theta, right? That's the number of degrees you rotate over delta t. Okay? So it's motion but in an angular direction. And we can replace I with mr squared. This is for some kind of rigid body with a uniform mass distribution, for example. Or maybe it's just our hollow cylinder that we raced the other day, times omega. Who remembers what the expression, the relationship between omega and the radial velocity is? I guess I could write that over here. The radial velocity is equal to r times omega. This is for very simple systems. Complicated distributions of matter, it would be a bit different. But we're going to only consider very simple symmetrical systems like wheels and cylinders and stuff like that. This is the relationship. It comes from S equals r theta, which is really just the circumference formula, the distance around the circle, over a limited angular region, right? From 0 to maybe some number of radians of rotation. So if I introduce this in here, then we're going to get m. We'll have r squared times v radial over r. One of these r's will cancel, and so we just have this. Let me illustrate this on the board. And I'm going to do so in 3 dimensions, because again, it turns out to be important. So here's the x-axis, here's the y-axis, here is the z-axis, coming out of the board, so to speak. If I put a particle here, a piece of test mass, this is a piece of mass, right? And I'll draw a vector from the origin to that point. This, by the way, the origin is our rotational axis, okay? And in this particular case, I'm going to assume that it is rotating about the z-axis. So it's the axis that's coming out of the board, right? So it's rotating in the xy plane, if you will. You have to kind of picture that in your mind, what's going on, right? Can you see that?
Yes.
So here it's the z-axis is drawn in a way that you can almost imagine a box, a cube being here. This is the corner of the cube, right? So we're coming out. You understand?
I think so.
Sometimes it's not the easiest thing to see, but yeah. Now the velocity is going to be quite general. I'm just going to draw a general velocity vector here, v, okay? For which that's going to have a component. I'm going to draw it right now. It's not the easiest thing to draw. This is a 90-degree angle. So I basically just extended the radial vector out, right, past the point of the mass. So here's our little m right here. And here's the velocity vector. This component here is tangential to if you can see the circle kind of going around. I'm trying to draw what it looks like. That's a terrible circle there. You can kind of see what it's doing, right? It's rotating around this way, yes?
Yeah.
And so the component of the velocity that contributes to the radial motion is, again, that component which is tangential to this curve, right? This rotation would be like this. But it's a little bit easier to see what it is if we look at it over here, right?
Yeah.
I'm actually going to erase it so it doesn't get too cluttered. So the angle between the radial vector and the velocity vector, theta, right? Which trig function do I need to multiply by in order to get this? I want to get VR equals, it's going to be the magnitude of V, right, times either the sine or the cosine to give me this component V sub r over here. Sine is opposite over adjacent, sine is opposite over the hypotenuse, right? You can see because this is our 90-degree angle, this velocity vector is the hypotenuse, right? I guess I should have probably drawn it all the way out to the end, like this. This is making a 90-degree angle to the radial vector, yes? Rob, how about you?
Cosine?
Well, that would give me the adjacent component, right? If I took the magnitude of the velocity vector, which is the hypotenuse of this triangle, right, and multiplied it times the cosine, I would be left with the component here. That's the radial component. That does not contribute to the rotational motion.
Oh, I thought that's what you're talking
No, I want the other one. I want the tangential component.
about. Sine.
Sine. Yeah, so VR times the magnitude of V times the sine of theta. So that's what we want to do. So I want to replace V sub r here in this expression for the angular momentum with m times, and this time I'm going to write it as a vector. So I'm going to write L vector because the angular momentum is a vector, okay?
Okay.
It's the r vector. Well, it's the hold on, I'm getting ahead of myself here. It's going to be equal to the magnitude of the r vector times the magnitude of v. It's getting messy. Times the sine of theta, okay? Where this magnitude of v times the sine of theta part, right, is there because I replaced v sub r, the radial component of the velocity, with this, okay? So this is assuming that you give me a general velocity. You haven't specifically picked the tangential velocity only. Why do I keep writing it with a subscript r? That's really dumb. This should be the subscript t, because it's not the radial component. Sorry about that. It's a little confusing, huh? This is the tangential component. That's what contributes to the rotation, right? That's probably why I put the r in there for rotation. So let's look at something else for just a minute. Does anyone recall what the area of a parallelogram is? Let me draw a parallelogram. Parallelogram. I don't know if that's spelled right. You'll recall that a parallelogram, it's kind of like a rectangle that's kind of skewed, right? There's a parallel side here, parallel side here. This side is parallel to this side. That's better, okay? So these two sides are parallel and these two sides are parallel, okay? Does anyone recall what the area formula for that is? If you can imagine me sliding this top piece over without changing the distance between these two parallel lines, then you can see that eventually it would turn itself into a rectangle, right?
Yes.
Yeah. And in that case it would be this height times the height of the rectangle. But that would, of course, straighten this line up, right? So if I draw a dotted line straight down from here, it makes a right angle with this guy, and we call that the height of this parallelogram, right?
Yeah.
And we call this the side length A, and we call this the side length B. Actually, yeah. Yeah, I'm gonna let me change those labels because I want to write a formula. I'll write this lowercase a, lowercase b. So side length A, side length B. The area, this is why I got rid of that A, the area is equal to the base times the height. Okay?
All right.
It's just a rectangle. And the way to see it is, again, if you straighten it up so it's no longer skewed like that, so this angle between A and B becomes 90 degrees,
Yes.
right? Of course, you'll shorten A, right? That's going to happen because I want to keep this height the same. But, yeah, so that's the formula for the parallelogram. The area of that's the formula for the area of a parallelogram. That's tough to say. Remember, vectors, you can slide them around, right?
Yeah.
So, for example, I can take this velocity vector and put it, well, it should roughly look like the same vector though, right? So I can take this vector and I can slide it down over here, right?
Yes.
Yeah?
Yeah.
And I could take this radial vector, which is a little bit longer than this guy, and I could slide it over here, just like this. Give it a little bit longer, so I'll do that with it like so, right? And now what I want to do is I want to construct a parallelogram out of this, okay? I'm going to take this radial vector here, I'm going to reproduce it up here. So I'll make it, maybe I'll choose a different color. It's exactly, I'm going to just make a copy of this bottom vector, r, right? And then move that copy up here, like so. And I'll do the same thing with v. I'll move a copy of v over here, like so, right?
Yeah.
So this is r, this is v, this is the angle theta, same angle that you saw over here, right? Now we have a parallelogram, right?
Yeah.
Now if I were to ask what is the height of this parallelogram, what I would do is I'd draw a line that is perpendicular to r down like so, right?
Yeah.
What is that height? I'm just going to call it height for now, right? The height would be equal to v, the magnitude of v, that's the hypotenuse, right? The length of this line here, times the sine of theta. It's opposite over adjacent, right?
Yeah.
But that's exactly what we call the tangential component of the velocity, you see?
Yeah.
And so here, I'm multiplying it by r, right? In my original formula for the angular momentum. So that tells me something, right? R times v sine theta, that's equal to the area of this parallelogram. Okay?
Okay.
Now, surfaces, unlike lines, right? If you want to give them an orientation, because I can take a surface and I can orient it in many different ways, right? Orient it like this, I could tilt it like this, I could tilt it like this, make it thin on one side so when you looked at it it was very thin, or make it very large so that you see it flat, right?
Yes.
And to describe that orientation, how do we do that? Any idea?
No.
No? Well, let me give you a hint. We're going to use another vector. But we can't use a vector in the plane of this thing, right?
Yeah.
What we use instead is a vector that's perpendicular to this plane. We call it a normal vector, okay? So now, if you see me rotating this around, you can see what the orientation is, right, based on this normal vector. Yes?
Yes.
Right?
Yeah.
So this plane will have a normal vector. And I said that the angular momentum is a vector quantity, right? The magnitude of this is the area of the parallelogram made by the radial vector and the velocity vector, okay?
Okay.
But it has a direction, and its direction is perpendicular. So in this case, since this is all in the xy plane, the normal vector to that will be in the z direction, right, coming out of the plane. And this is the angular momentum, L. So the angular momentum is coming out of the plane. So if you think of like a bicycle tire, and you hold it and you let it spin, such that it spins like this, right?
Yeah.
Its angular momentum is directed straight up. If I tilt the bicycle tire, the angular momentum tilts, okay? This is really just a way to keep track of the orientation of that plane, okay?
Okay.
The plane of rotation in this case. We have a definition that we can use here. Let me show you that here. So when we have, let me just redraw my parallelogram real quick. Magnitude of r times the magnitude of v times the sine of theta, where this is theta, right?
Yeah.
We define this as r cross v. It looks like your traditional multiplication symbol. Usually it's written a little bit bigger, a little bit darker, okay? It's called the cross product, okay? And you may recall we talked about another vector product before, the dot product, right, which is scalar. It doesn't have a direction. The dot product is a vector, and it has a direction. It's always perpendicular to both r and v, okay?
Okay.
And so for that reason, we can rewrite L as m times the magnitude of r times the magnitude of v times the sine of theta. This area, which also has a vector component to it, right, we can call r cross v. Okay?
All right.
Now this is just a multiplication, and scalar values, right, will distribute through it, no problem, right? So I can move this mass over here in front of the v, so I can rewrite this as r cross m times v, okay?
All right.
Because multiplying a scalar times a vector just makes the vector get longer, okay?
Yeah.
The direction doesn't change. mass times velocity, you recall, is momentum, right?
Yes.
So this is r cross p as a vector. Okay?
Okay.
So to figure out which way the angular momentum is directed, right? Because if I showed you before that if you have a plane, you can think of a normal vector like this, right? But this is also normal to it, right?
Yeah.
So there are two possible orientations, in the positive direction or in the negative direction. And the way that you determine it is using something called the right-hand rule. So let me show you that now. If you, for example, if this is the r direction, okay, this way, and the v direction is, say, this way, right? The way we figure out which way the angular momentum is going to point, either out of the board or into the board, we take our fingers, okay, and we allow them to curl the first vector, r, into the second vector. Well, maybe I'll make this p. Linear momentum p, right?
Yeah.
And when I curl the first vector into the second, the direction that my thumb is pointing tells me which way the angular momentum is pointing. So this is coming out of the plane, that'd be positive z. Okay?
Okay.
If I switch these guys, right, and make this the momentum and this is r, right? Now, when I curl r into p, right, you can see my thumb is pointing into the board. So that's the negative z direction. Okay? So it's the right-hand rule that determines which way the vector points. Now, you probably won't have a lot of occasion to use that immediately, but later, as you get into more physics, it'll become useful. As a consequence of this, it has the interesting property r cross p is equal to minus p cross r. Okay?
Okay.
So another way to say that is that r and p don't commute. Remember the commutative property?
Thanks.
So for example, if I multiplied x times y, that's the same thing as y times x, right?
Yes.
So 2 times 3 is the same thing as 3 times 2?
Yeah.
Well, for scalars, things multiplication commutes.
All right.
Okay? Cross products, which is it's a vector product, right?
Yeah.
They do not commute. Okay?
Okay.
I think that is all I wanted to tell you. Next time we'll talk about the analog to Newton's second law, force equals mass times acceleration,
Yeah.
right? And we'll be talking about torque, which is the angular analog to force.
All right.
Okay.
See you next time.